So I forgot a contribution to this Bianchi identity here. So if you tried this exercise, you found probably something missing. And there is an extra term that still vanishes if you use the condition of vanishing torsion. So it is proportional to the torsion, but there is a second term besides this one. So let me make room for that. So the second Bianchi identity, I think, is complete. So it's like this. So the first Bianchi identity is this right-hand side plus cyclic permutations is equal to del x t yz plus t x commutator yz plus permutations t x commutator yz, and this should be completely general. So permutations are cyclic permutations of x, y, and z, so you have to write three terms, three copies of those terms. And in the first one you send x to y, y to z, and z to x. And the second one you do the permutation twice. There was another place where we wrote that. This was when we derived the Bianchi identities by means of differential forms. It's a very different approach, and the Bianchi identities written that way bear some similarities with those on vector fields, but there are some differences, as we have seen. Anyway, let me see if I find the other place. Yeah, probably this is a lot earlier than I need to. Okay. Well, it was the other place where we wrote the Bianchi identities. Contracted Bianchi identities, no. Here. Yes. Here I copied that Bianchi identity with the missing term, so again there is t x commutator y z. So with vector fields you have to do that. When you use differential forms, instead you have this Bianchi identity del t is r wedge e. So it appears that this thing disappears, but this is because we're using vector fields. And again, the identity, the Bianchi identity, the second one is much simpler with differential forms, because you just have del r equals 0. Okay. Now the exercise, I think, is straightforward. So today we discussed the gravitational action. Let's start by first we complete infinitesimal transformations. We have seen the infinitesimal transformations of the spin connection, which is a covariant derivative, and as a form, so it doesn't change under diffeomorphisms because it is a form. It just changes as the covariant derivative of the parameter theta. And so if you want to write the transformation of omega as a form, in components. You have the transformation of omega as a vector, as a form, actually. So it has lower indices. So we should transform the Latin index mu pretty much as we did for the generic vector, which is that thing. So you have a contribution that's like this. Then the second contribution, because it's a vector, the first contribution is the one that you have for scalars, for everything actually, and the second one is the one that you have depending on the properties of your field. So in this case it's partial mu psi rho omega rho AB, and then you have minus, in that notation, del mu theta AB. So this is the complete transformation, infinitesimal transformation of the spin connection. If you want, we can also derive, so this is plus higher orders. When here I have dots, it doesn't mean that there is something missing, simply means plus higher orders. It's better to write it down explicitly. So the infinitesimal transformation of the field line is this one. Yes, so let's write, instead of omega prime equal to, let's write delta omega, because otherwise we have to add those corrections. So delta omega is this one. Delta E mu A is what? It's this. And then we can write something we already know, but it's better to write it down from here. That is the transformation of, infinitesimal transformation of the metric tensor, and that is derivable from the one of the spin connection by the definition, by the relation between the metric and the spin connection. So here there are, it's symmetric, the eta EB is symmetric, so you can write 2 E A mu eta EB delta E B nu, and that is equal to 2 E mu A eta AB psi rho partial rho E nu B B nu plus partial nu psi whatever rho partial nu psi rho E B rho plus theta AB E B theta C B C E C nu. Okay, so obviously the contribution here with theta goes away, because when you lower the index due to the eta AB, you have theta AC, which is anti-symmetric. And yes, so instead of writing this shortcut, I should have, instead of writing 2, because this is not symmetric, not manifestly symmetric, let me just write this plus its symmetrization. So we do not risk anything doing that. Okay, so the term with theta after the symmetrization in mu and nu is drops because theta is anti-symmetric. Then after symmetrization, this thing becomes psi rho partial rho acts once on one field plane, once on the other, so the sum of the two is a total derivative, and it comes to act on g mu nu. So that is g mu nu, the usual contribution. And then you remain with two other contributions, which we can write explicitly: partial nu psi rho e mu a eta a b e rho b plus partial mu psi rho e nu a eta a b e b rho. But this is again g mu rho, so you get, as usual, as we know already, the derivative of the metric. Now, this combination can hold under certain assumptions if the torsion is zero and the metric is compatible with the connection is metric compatible, then we can also write this as this thing, covariant del mu psi nu plus del nu psi nu, where psi with the lower index is just psi with an upper index times the metric, so that its index is lowered. But the final form here, which may be useful in some situations, and we will see later when, well, we'll just give an example, that equality holds only if both assumptions we have made here hold. Why? Because let's just write this explicitly and check that it coincides under those assumptions with what we get up there. So this is partial mu g nu rho psi rho. Then there are Christoffel symbols, and you get this. And then you have the same thing once you exchange mu and nu. Okay, so let's perform that derivative. You have two contributions, partial mu g nu rho psi rho plus g nu rho partial mu psi rho. In the second, yes, we could write, the second we write explicitly because you know that if those two assumptions hold, gamma nu rho is 1/2 g rho sigma partial mu g nu sigma plus partial nu g mu sigma minus partial sigma g mu nu. And so let's write that. So we have g rho sigma psi rho that just raises the index of psi, which is lower here. So with g rho sigma it gets raised and you get psi sigma. So you have 1/2 psi sigma and the rest. And again, we have to symmetrize in mu and nu. So what do we get when we symmetrize the first two terms? We just copy them. G nu rho partial mu psi rho. Then we have plus partial mu G mu rho psi rho plus G mu rho partial mu psi rho. And when we symmetrize the other term, which is symmetric already, we just drop 1/2. So we get psi, let's say rho partial mu G nu rho plus psi rho partial mu G mu rho minus psi rho partial rho G mu nu. So what do we have here? Let me see. So this is okay, this is okay. Oh, I think that yes, these are lower indices. These are lower indices, so the covariant derivative has a minus sign in front of the Christoffel symbols. Because remember that the covariant derivative is basically d plus gamma, but gamma has those two indices, so if you act on an upper index you have plus, otherwise you have minus. So let's see if this gives the right result. We have to change the sign there, and we have to change the signs here, and plus. So these three in column are the ones we expect, and the other two should cancel. Let's check. Psi rho partial mu, this cancels with that, and this cancels with that. Okay. Now, a vector psi mu such that partial mu psi nu plus partial mu psi mu equals 0 is called Killing vector. And describes an infinitesimal, because here we are in the infinitesimal transformation, isometry, which is a transformation that does not change the metric. That's why it is an isometry. So a transformation, infinitesimal or not infinitesimal, global or local, that does not change the metric, could happen if the metric is particularly has some symmetries, it might not change at all, even if you make a change of coordinates, then you say that that change of coordinates is an isometry. Now, we start with the gravitational action in the Palatine form. And in so-called first-order formalism. What is it? So the action is written with the field bind and the spin connection, and apart from the constant, which we will determine from a certain normalization, it is equal to the integral on the manifold M of what? Something that can be written by means of differential forms, and it is like that: RAB wedge EC wedge ED times epsilon ABCD, where epsilon is the completely anti-symmetric tensor, and RAB is again the form we are familiar with already. In that case here we just raise the right index. That is a four form, so it's a volume form, and once we convert it to the more common notation, we find that this action is equivalent to the action you are familiar with, which is due to Hilbert, and so we call it Hilbert action. So it's proportional to the integral on m square root of minus g r d for x. This is in 4 dimensions. Why is that? Well, to see that, it's sufficient to expand the two form there in a basis, let's say Mn. We can use a basis of made with a field bind. We could use space-time indices, depends on what. We can always convert from one to the other by means of the field bind. So let's do that and show the equivalence of these two actions. So the Palatine action is equal to C times the integral on the manifold M of R, A, B, Mn, E, M, E, N, E, C, E, D, epsilon, A, B, C, and D. And there is a 1/2. Now, this object is a four form. They are forms, so they are completely, they are anti-symmetric when you exchange any of the two. So this object must be completely anti-symmetric in Mn, C, and D. So let's isolate this and write it in a more convenient way. So this must be proportional with certain index A to epsilon m n c d. And we can also write this as E m mu, E n nu, E c rho, E d sigma, dx mu, dx nu, dx rho, dx sigma, epsilon a, b, c, d. Again, this is easier. This must be proportional to epsilon mu nu rho sigma, because it is completely anti-symmetric. And when we choose, for example, mu nu rho sigma equal 0, 1, 2, 3, and remember epsilon 0, 1, 2, 3 is 1, then this must be dx0, dx1, dx2, dx3. So that's what it is. That's how we convert the volume form into the normal volume integral. Therefore, here we have our d for x. That multiplies those things that you find there. Okay? Now, if we want to find A, it's sufficient to multiply both sides there by epsilon mn cd. And use the fact that epsilon mn cd, epsilon mn cd is equal to minus 24. So from the right hand side you have minus 24a, and from the left hand side you have epsilon mncd times that thing. So let me copy this thing. It is equal to d for x epsilon mncd. Oh, sorry. MNCD, yes, there is no tensor there. This is completely anti-symmetric, so whatever it is, it is. It has 4 indices, so on and so forth. So you don't need to include, we will multiply later by epsilon ABCD. When we go back to the formula here. For the moment, we just consider this object that I wrote, that I underlined here. This is completely anti-symmetric in MNCD. So we have d for x, epsilon MNCD, and then we copy this. Now you might have recognized that this is a way to compute the determinant of the matrix. The determinant of the matrix is what we called E, and this is minus 24E. So it's minus 24 E d for x. which means that A is just square root of minus g, if you want, d for x, or E d for x. Therefore, we can replace this object here with epsilon mncd times E d for x. So, Palatine action is c divided by 2 integral on m of r a b m n. Say E, we can write it there, a b m n epsilon mncd, and then the other epsilon abcd. And now we're done, because the contraction of two indices of the epsilons is very easy to compute. So R, A, B, M, N, and this, you know, is minus 2 times a bunch of delta functions. So it's delta MA delta NB minus delta MB delta NA. And minus 2 and 2 go away, so you have minus C. When you contract A with M, you obtain, first with third index, you obtain the Ricci tensor, and when you further contract N with B, you obtain the Ricci scalar. And I forgot D for X, which can be left understood now, but for the moment, let's write it explicitly. When you contract the other way, you get again the Ricci scalar, because this is anti-symmetric in M and N, so you have twice the same contribution. And so you see you have the Hilbert action. The Hilbert action will be normalized as follows for various reasons. S Hilbert equals minus 1 over 2k squared integral square root of minus g r d for x. And that means that the Palatine action is equal to minus 2c minus 2k squared, the Hilbert action. So it should be equal, of course, to the Hilbert action, which means we choose c equal to 1 over 4k squared. And that is the Palatine action. Written in a nice way by means of differential forms. But actually, we are using indices, so we are not writing it in a completely intrinsic way, because we are still using indices for the tangent space, for the flat space indices. However, we do not need to use space-time indices. We can write in a similar way also the cosmological term. And that is the integral on M of EA, EB, EC, ED, epsilon, A, B, C, D. It's proportional to that. And the constant in front will be normalized to have what we normally write together with the Hilbert action. Again, we can use thing we wrote previously here. We know that the product of those four is equal to E d4x epsilon. So that is M E d4x epsilon ABCD epsilon ABCD, which is minus 24. So this is minus 24, the integral d4x square root of minus g. So this way we can normalize the cosmological constant. Normally the Hilbert action with the cosmological constant, which we might call Einstein-Hilbert action, because Einstein was the one who introduced the cosmological constant, can be normalized. So this is a convention that we will adopt like this. R, which is scalar, plus 2 lambda. And if we want, well, we know that the first one is C, big C, which is 1 over 4k squared, integral over M of R, A, B, E, C, E, D. And then the other one we can check is equal to lambda. Probably it is this. Now we will check EA, EB, EC, ED, epsilon A, B, C, D. Well, we could have collected these two actually, moved them outside, compactified the action a little bit more. Let's see, lambda divided by 6 means lambda divided by 24k squared, but that means minus 1 over k squared, which is okay because here you have minus 1 over 2k squared, plus here you have plus 2. So that is a way to write the, let's call it Hilbert-Einstein action. Well, still we have not said much. There were about this action. We just have found that it corresponds to the usual one, but when I introduced Palatine action, I said first order formalism. What does that mean? What is the first order formalism? First order formalism means that we consider the field bind and the spin connection as independent variables. That's what it means. Second order formalism is where instead, if you assume certain assumptions, we will see which ones, the spin connection will become a function of the field by. And so you just have one independent field, the field by, or the metric. Now, what assumptions do we make in the case of the Palatine action? We assume metric compatibility but not vanishing torsion. So metric compatibility means this, or if you want, omega is anti-symmetric when you raise both its indices. But we do not assume vanishing torsion. Because if you assume both, then the spin connection is not free, it is dependent. It depends on the field bang, as we know, and so you cannot use the first order formalism. Instead, what we do now, for the moment, is to assume metric compatibility but not vanishing torsion, treat EA and omega AB as independent variables, perform the variation with respect to both to work out the field equations, show that the field equations of omega can be solved, and they give vanishing torsion. So vanishing torsion comes out of the field equations obtained by varying with respect to omega. So let us see that. Let us rewrite Palatine action more explicitly in terms of E and omega, because we know what R is. We do not consider for the moment cosmological term, can be added later. So what is it? It's 1 over 4k squared integral on M of what? R, which is this, E epsilon. And so when we make a variation with respect to omega, we just vary inside here, inside the curvature. And when we study the variation with respect to E, we vary just those two terms. So let's start from the variation with respect to omega. Let me write here the variation of the curvature itself, because that's all we need, and because that's particularly simple. The variation, well, first the variation commutes with the covariant derivative, with not the covariant derivative. There is no covariant derivative here. With the exterior derivative, because the exterior derivative of this is, of course, that, and so you can interpret this thing as the variation of d omega. And then you perform the variation. So the variation is a bosonic operation, just to raise any doubt about that. D is an exterior derivative because it has a differential, but the variation is a full variation. Omega and omega plus delta omega have the same statistics. Delta cannot change the statistics. And then you have this. So this is the variation. Well, as we saw in the other time, this conspires to build something interesting, the covariant derivative of the variation. So in a curvature, there is no covariant derivative because the curvature is a primitive of the covariant derivative. When you vary the curvature, you get the covariant derivative of the variation of the connection. Why is that? Because let's remember the definition of covariant derivative. Omega has two indices like that. So the definition of covariant derivative says that as far as the left index is concerned, which is raised, you have an omega 2. So this is covariant derivative of delta omega. So as far as the left index is concerned, you must multiply by omega to the left. And as far as the right index is concerned, since it is lowered, you must add something like that times multiplication to the right by omega, where k is the degree of omega itself, or delta omega. K is, in our case, 1, and so you get omega delta omega plus delta omega omega. So that's precisely the covariant derivative. So the variation of the Palatine action is equal to 1 over 4k squared integral over m del of delta omega, and that will have indices a and b. A and B, we have to write them that way, so one way lower. Then we have EC, ED, epsilon, A, B, C, D. Now we can, of course, raise and lower the indices inside and outside the covariant derivative. That we can do. Why? Because we are assuming metric compatibility. So that's something we can do, but for the moment we can, for the sake of precision, start from this formula, which is very precise, and then we will see how to manipulate it. So we start again in 10 minutes.